Unit 4 Kinetics and Mechanism of Substitution Reactions of Octahedral and Square Planar Complexes. Welcome to Royal Chemistry Park, the YouTube channel. I am Dr. K. Rajarajan, Associate Professor and Head of the Department of Chemistry, Raja Sarfuji Government College, Tanjavur. In this video, we are going to see the trans effect and the theories of trans effect. Now let's get into the video. Let's first define what is meant by trans effect. The trans effect gives the relationship between the reaction rate and the nature of the ligand trans to the leaving group. The ability of a group to direct substitution into its trans position is nothing but called as the trans effect. So in the screen, now you are seeing 3-chloro and 1-amino platinate square planar complex. When this square planar complex is allowed to react with an alkene, that is ethylene, one of the chlorine is getting replaced by the C2H4 group. Here, the chlorine, which has a greater trans effect than the ammonia cannot replace the chlorine because the trans effect of this ammonia is greater than this ammonia. So that the group which is cis to this ammonia, that is the chlorine, is replaced by the ethylene. So you will get dichloro 1-amino and 1-ethylene platinum complex. Here you are having 3-chloro and 1-ethylene platinum complex. This square planar complex, when it reacts with ammonia, here you can see the ethylene replaces this chlorine and ammonia is getting substituted in this place of chlorine. Here the group which is trans to this ethylene, that is chlorine, is lesser trans effect than the alkene. So that when this C2H4 has greater trans effect than chlorine, this will be getting replaced by the ammonia, so that we will get the trans product. So the trans effect can easily determine the formation of products of following reactions. So substitution of chlorine ions from tetrachloro platinum complex by ammonium. So initially we are having tetrachloro platinum complex. In this, platinum is the central metal ion and we have all the 4 chlorine atoms identical to the platinum. This charge is 2 minus. When this is allowed to react with one molecule of ammonium, let's see what will be happened. Since all these 4 chlorines are identical, one of the chlorine is replaced by the ammonia. Now this trichloro 1-ammonia platinum complex when it is allowed to react with another molecule of ammonia, here we are having the two probabilities, that is the two chances, which one will give the product. Now let's see that. So in the first case, we will have cis product. Here the another probability is trans product. Here the trans effect of chlorine is higher than ammonia. Actually, you can see the two chlorine atoms here. The question is, which one will be getting replaced? Whether this chlorine is replaced or this chlorine is replaced. If this chlorine is replaced by ammonia, you will have the cis product. If this chlorine is replaced by the incoming ammonia, then you will have the chance of getting this trans product. But in actual conditions, what is actually happening is the trans effect. Which one will have the higher trans effect? Here, the chlorine is having higher trans effect than the ammonia. That is why it will form the cis product. So that one of the chlorine is replaced by the ammonia and you will have the cis product. Here, since this already we have stated that the chlorine is having a higher trans effect than this ammonia, this cannot be replaced by the ammonia as in the case. So that the formation of trans product is not possible at all here. Now let's see the substitution of ammonia from tetra-ammonia platinum complex by chlorine. So in the previous case, all the four ligands are chlorine. Here we are having all the four ligands are ammonia. So when all these ammonia are identical and when this is allowed to react with uh, chlorine ligand, one of the ammonia will be replaced by one chlorine and resulting the complex like this. That is 3 ammonia and 1 chloro platinum complex. So in the next step, trans effect of this chlorine is higher than ammonia. So already we have stated that the trans effect of this chlorine is higher than the ammonia. Here this chlorine replaces ammonia with the incoming Cl, so that you will have the product like this. So that this is what called as trans. Here you are having cis dichloro, cis diaminoplatinum, which is not actually not possible. There is no evidence of having such type of products because it purely depends upon the trans effect of the substituents. Here, since chlorine has higher trans effect than ammonia, this will easily replace this ammonia with another molecule of uh, uh, chlorine. The formation of these products are governed by the substitution of ligands in the square planar complex. Trans to Cl ions are called as trans effect. The group that directs the substitution trans to it called as the trans directing group. And now you are seeing one of the groups, the series of groups uh, that will give the trans directing ability. So the trans directing ability is given as cyanide, carbonyl, nitrosyl, and ethylene. All these four ligands have equal trans effect, and these trans effect of these four groups will be higher than thiocyanate and hydride and substituted phosphine. The thiocyanate, hydride ion, and the phosphate and substituted phosphine, these are the ligands which are having the next category of equal trans effect. So these groups have greater trans effect than uh, iodide, thiocyanate, chloride, chloride in turn, which is having a greater trans effect than pyridine, and the substituted primary amine, which is having more trans effect than ammonia. This ammonia is having higher trans effect than OH minus, and this OH minus is having higher trans effect than water. So these are the series of ligands depending upon their trans directing ability. Now you are seeing this dichloro XY platinum complex. Here, if the X is having the greater trans effect than Y, then you will have uh, the product like this. Instead of that, if Y is having the maximum trans effect than X, then you will have the product like this. So it has been observed that the trans directing ability of ligands such as carbonyl, CN, nitrosyl are higher because of the presence of vacant pi or pi star orbital for accepting electron from filled metal orbital to form d pi d pi or d pi p pi type of metal ligand bonds. The pi bonding ability is directly affects the ability of trans effect. More will be pi bonding ability of ligands, higher will be the trans effect. So that we can say that the pi bonding ability and the trans effect are directly proportional to each other. When one of the factor getting increased, the trans effect is also getting increased. However, the ligands such as water, ammonia, chloride, etc., actually in this type of ligands, there is no pi bonding ability. That is, these are the ligands which are having the lack of pi bonding ability. Their trans directing ability in this case is governed by the polarizability. Here, polarizability directly corresponds to the trans effect. It means if higher will be the polarizability, more will be the ability to trans effect. Now, let's discuss some of the theories on trans effect. Actually, there are two theories. One is polarization theory and the other one is pi bonding theory. Let us first discuss the polarization theory. Actually, the trans effect is a kinetic phenomenon affecting the magnitude of activation energy of a reaction. The kinetic trans effect is different from ground state or static trans effect. This affects physical properties such as vibrational frequency, bond length, and chemical strength. There are two main theories which can explain the phenomenon of the trans effect. So, as I stated earlier, let us discuss the polarization theory now. According to polarization theory, the effect of sigma bonding of a ligand would be directly related to its trans effect. In case of tetra-X platinum type of complex, it means the platinum will be in the central position, and in the four corners the X will be ligands connecting the platinum ion. So the overall dipole moment generated will be zero, and hence no trans effect are observed. That is the case for the platinum tetra X type complex. Instead of that, suppose if you have platinum LX3 like this. Platinum LX3 means one central metal atom of platinum, and other three ligands are one type, and one different ligand in one of the positions. So if this type of complex, then what will happen to the dipole moment? So the dipole moment across the same ligands, that is trans to each other, XX, that dipole moment cancels each other, and so no trans effect observed. But the L and X, which are opposite position, the two ligands L and X, when they are kept in the trans position to each other, their dipole do not cancel each other, so that due to larger size, L has higher polarizability than X. The induced dipole of L causes deformation in platinum 2, results more effective bonding and higher bond energy in L platinum than platinum X trans to it. This results platinum X bond trans to platinum L bond are weakened and longer. The weakening of PTX bond trans to PTL bond causes the rate of substitution of X more easily. It is evident that due to higher polarizability, L has higher trans effect than X. In the figure, we have depicted the electrostatic polarization in platinum 2 complex. So, greater the trans effect of L, that will result MX bond weaker and longer, so that the bond getting elongated and becomes weaker. The trans effect of the ligands which are not able to form metal ligand pi bond increases with the increase of their polarizability. That is the order of polarizability increasing from chlorine to iodine. So when polarizability increases, the trans effect increases. So bromine will be more polarizable than chlorine, and iodine in turn having more polarizability than the bromine. So that accordingly the trans effect will also increase. Now let's see what is the pi bonding theory. The ligands having vacant pi or pi star orbitals can accept electron from filled metal orbital to form metal ligand pi bond. So the pi bond may be d pi d pi or d pi p pi bonds. So these ligands are therefore called pi bonding ligands. For example, carbonyl, cyanide, alkene, substituted phosphine, etc. The trans-directing ability of the pi bonding ligands increases with the increase of their ability to form metal ligand pi bond. For example, in the case of PTLX3 type complex, the formation of pi bond increases the electron density on the platinum L bond and decreases on trans of L. This results the PTX bond trans to PTL bond weaker. Hence, substitution goes to X trans to L. For example, in the case of PTLX3 type complex, the formation of pi bond increases the electron density on the platinum L bond and decreases on trans of L. This results the PTX bond trans to PTL bond weaker. Hence, substitution go to X trans to L. Here you are having PTX3L type. So when this is allowed to react with Y, you will have the structure like this. Here X means chlorine. So here actually the bond associated with X is getting elongated due to the polarization effect of L, so that this will be getting detached from the complex and the incoming ligand Y will be substituted trans to L, so that you will have the structure which is like this. The trans platinum dichloro di L and Y ligands, so that this is due to the trans effect of L. The pi acceptor ligands increases the stability of reaction intermediate, that is trigonal pi pyramidal. The incoming Y enters into the direction of platinum X bond trans to L because of poor bonding of this bond with the platinum 2. The d pi p pi bond and d pi d pi bond formation is shown below. So the in the picture you can see how the d pi p pi bond is formed. So the overlapping between vacant p orbitals of the ligands and the filled d orbitals of metal ions made it possible. So in this figure, this is what called as d pi bond. Here, overlapping between vacant d orbitals of ligand and filled d orbitals of metal ions form this figure. So what we have seen so far is initially we have seen what is meant by trans effect. So the trans effect gives the relationship between the rate of the reaction and the nature of the ligand trans to the leaving group. The ability of a group to direct substitution into its opposite position, that is trans position in the planar complex, is called the trans effect. The trans effect of the ligands which are not able to form metal ligand pi bonds increases with the increase of their polarizability. The trans-directing ability of the pi bonding ligands increases with the increase of their ability to form metal ligand pi bond.